In this video, I really want to express my deep dissatisfaction with the way math taught in schools. It's really when we learn a new topic, teachers just make us memorize the procedure to solve a particular type of problem. As long as you memorize it and you can follow the steps, you can do well on the exam and you'll get good grades and you'll complete the class successfully. But does that really mean that you are understanding that topic on a fundamental level? So today, really, in this video, I want to go over a concept of a derivative, which is the first topic that you start learning when you take Calc 1 in high school. Now, but do you really understand what is a derivative? So imagine you have a function x squared. Okay, that's the simplest example we can make. And usually when we are working with functions in a 2D coordinate plane, right? We have two axes. We have x axis and we have y axis. So we need two values that we're looking at when we want to graph this function. Now, in order to compute x squared, right, first you'll take a value for x, which falls on the x-axis, and then x squared is your output that you're getting by passing the input value through this function. So in this case, it's a squaring function, right? So for convenience purposes, we'll introduce a second variable that we're using that expresses this function x squared. So we have y equals x squared. That's the relationship between these two variables. So you can choose any value for x. Let's say you choose 2. Then how do you get y from it? Well, looking at this relationship, we know that we have to square x. So 2 squared is 4. So when x is 2, y is 4, and so on. That is literally the definition of a function. It's a mapping between an input and output, and the function does something. The function is an operator in this case. Let me just make a quick graph. Like our classic x squared. Classic x squared function. All right. For the derivative, really, the question that we're asking is, when I change x, how does that affect y? Right? So let's say for a unit change in x, what happens to y? So in this case, when x is equal to 3, then y is x squared, so it's 3 squared, so 9, right? And then when x is equal to 4, y is actually 16. So in this case, for a unit change in x, y grows by 7 units. Now, I mean, why would we even want to know this change? Well, it can be useful when you have a dependency between two variables. And you just want to know, like let's say your x is time and your y is velocity or acceleration or something. So then really the question you're interested in is, for some change in time, how is that going to affect my velocity or my acceleration? And, that in turn can be useful for many other different applications. So that's really the question that you're asking fundamentally. You want to see these two uh, variables. One is independent x and the other one is dependent y. So for a change in the independent variable, how is that going to affect your dependent variable? Okay. Actually, let's just write it out explicitly first. So one major point is that we're talking about the notion of change, right? So now, let's say our x naught is initial x value, and then I'll say xf is final x value, and then and similarly y naught will be initial, and yf will be final. So now what I said before, we're interested in change in x. So x final minus x initial, how is that going to affect y, right? What's going to be y final minus y initial? Okay. And from your physics class, I'm sure you will remember the delta notation. Actually, you might already be familiar with this quantity, and that usually in science classes you will just say delta x. So delta x is literally x final minus x initial. And this big delta is a convention to express the difference between the final value and the initial value, right? So we have delta x and we have delta y, which is y final minus y initial. So now when I said that we have a unit change in x, right? Let's say x initial is 1, x final is 2. So delta x final minus x initial is 2 minus 1 equals 1. So we have a unit change in x. Now, how is that going to affect y? We know that y is a dependent variable, and delta y is y final minus y initial. But because y is a dependent variable, we can rewrite it in terms of x. So we're going to have x final squared minus x initial squared. So we're going to have 4 minus 1, 3. So we see that in this case, for a unit change in x from 1 to 2, we're actually going to have a 3 unit change in y from 1 to 4. So now if we're asking what is that ratio of change, right? So you're just going to divide the change in y compared to the change in x. So you could just express it as a quotient, delta y over delta x. For this specific example, is going to be 3 over 1, 3. So what is this number? Well, that's the change in y compared to the change in x for these initial and final values that we chose. Next question is, what if you want to know the rate of change as the change in x gets smaller and smaller and smaller and smaller? So now remember this notation precisely. And I hope that it looks very familiar, this quotient, change in y over change in x. You should have seen it before, right? Isn't it just dy over dx, right? If you know even a little bit about derivatives, then you know that this is the standard notation of the derivative. So really, derivative is exactly the same thing as delta y over delta x, but the convention is that we use this little d to represent a very small change. So it's pretty intuitive. We use big D delta to represent a big change, and we use little d to represent a small change. In fact, it's such a small change that it's almost zero. So we just say that it's instantaneous change. And ultimately, we want to see that change at a single point where actually the difference between the final and initial values approaches zero. So I'm going to start by saying let x final be x naught plus h, where h is a very small change in x. Okay. What we're asking is, how does that change affect y? Okay, so we can start again with this notation of delta y over delta x. So we can rewrite this based off of our previous definition as y final minus y initial over x final minus x initial. Okay, and now here, let me focus on the denominator first. Okay, so what is x final? Well, we just define it as x naught plus h, and x initial is just x naught. So I hope you can see clearly why our denominator expanded to this. So we're going to have x naught plus h minus x naught. And then in the numerator, it's just y expressed with x. So we're going to have x naught plus h squared minus x squared, like this. Now we are going to simplify it a little bit. Okay. So let's we're going to have x naught squared plus 2x naught h plus h squared minus x naught squared. And then in the denominator, x naught cancels, so we're just gonna have h. And finally, these two also cancel, so we're gonna have 2x naught h plus h squared over h. And we can simplify this expression further by canceling out all the extra h's. So finally, we're going to have 2x naught plus h. Okay, this is our final expression for the rate of change of delta y compared to delta x. Now, what if h gets smaller and smaller, and finally approaches 0. So following the convention, we can write this as dy over dx, because this little d tells us that we're interested in that instantaneous rate of change. So that's where we're going to use the definition of the limit, and we're going to say that we're taking the limit as h approaches 0 of this expression that we got here, right? So it's going to be the limit of 2x naught plus h. And this should be a very easy one. H approaches 0. This term just becomes 0. So we're left with 2x initial. First of all, I really hope that this result looks familiar to you, because if you learned about derivatives before, then you know that the derivative of x squared is 2x, which is literally what we got here. So this is telling us one thing. First of all, that as the rate of change gets smaller and smaller, obviously we get rid of that x final value. So it's not dependent on your final value at all. You just need your x initial, x naught that you're starting with. Second of all is that the rate of change is in y will always be twice as that as your value of x. So it's always this function of x. You need your value of x first, but by knowing the value of x, you'll always know the rate of change of y. And just to sum it up, I also want to bring up this notion that derivative is an operator, right? Just like anything else that you learn, addition, subtraction, multiplication, exponentiation, those are operators, something that you do on your input, and it produces an output. So there's many ways to express the concept of taking the derivative, but I personally believe that dy over dx is the notation that makes the most intuitive sense, because it shows you visually that actually you're looking at a quotient of the change of one variable compared to the other variable. So when we have the relationship between y equals, let's look at x squared again, y equals x squared. So if derivative is just an operator, and we have this equation, y equals x squared, then like any operator, we can apply it to both sides of this equation and then see what happens. So let's do that. Right? We are interested in the change in y compared to the change in x. That's our left-hand side. So what happens to our right-hand side? We are interested in change in this quantity, x squared, compared to the change in x. So we can write it as d of x squared over dx, right? And so for this side, we can't simplify it further, because we know that y is expressed in terms of x, and there's nothing we can do to simplify it, right? But this side, we're interested in the change of x squared compared to the change in x, because both of our quantities are expressed in x. This is simplifiable, right? So if we rewrite it, we have dy over dx equals 2x. We started with the original equation, then we applied our derivative operator. Left-hand side, we can simplify further. Right-hand side, we can. So right-hand side just turned it to 2x. And that's how we know that the derivative dy over dx equals 2x. And there are other ways to write the derivative. We can say y prime equals 2x. Sometimes we use y dot, a lot of times in scientific notation, also 2x. But I do think that dy over dx is the best way to write it, at least when you are just starting getting used to that concept. You really need to work it through a few times to get that intuitive sense of what is it that you're doing. All right. I hope this video was helpful to at least someone, and I really hope that you developed a better conceptual and fundamental understanding of what a derivative is.